Hey there, in this video I want to talk about one more technique for solving nonlinear equations, and that's called the Newton-Raphson method. The setup for this is to put your nonlinear equation in the form f of x equals 0, just like we did with binary search. And we're going to call our solution x naught. So let's look at what would happen if we Taylor expand around the solution. So we're offset some amount x, where x could, like, say, represent a close guess. Then the Taylor expansion around the solution is going to look like f of x plus solution minus guess, first derivative at x plus dot 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 dot. And then by definition, f evaluated added solution's got to be 0. So now we can rearrange this and drop higher order terms, and we're going to find that f of x is approximately x minus x naught times f prime at x. And now we can solve that for x naught, finding that x naught is approximately x minus the function at our guess divided by the first derivative at our guess. And so our technique for solving, since that's only approximate, is we're going to iterate. So our new value of x is going to be our old value of x minus f evaluated at the old value divided by the derivative at the old value. Now, when it comes to technically being Newton-Raphson, it needs to be an analytic derivative here. You have to know what the derivative of the function is as a function. And so if that's known, you can put it into your code. That's Newton-Raphson. But, can't we just numerically calculate derivatives? Haven't we learned how to do that? And yeah, we can do that. So as long as we have the function f, we can calculate approximately what its derivative is numerically. And so if you calculate, that's technically called the secant method. But the two methods are extremely similar, so we just kind of lump them together here. And if we make a picture of what we're doing with this technique, it's really kind of cool. So let me draw the function here in a different color. So let's just say here's a segment of f of x, and we know we have a solution right here. That's our root x naught. And so we make some kind of guess. Let's just say we guess over here that this is our solution. This will be like our first guess. Okay, so we come up here to x, and what we're doing is basically looking at the ratio of f of x on its derivative. And what that does is it sends us down the slope, the derivative here, to hit a new value. We'll call that x2, and then we jump up and we ride down the slope. That would be x3, and then up and down, up and down. So we sort of like zigzag in on the solution. And this can be actually very quick. The only place we're going to get burned here is if the higher order terms, the second derivative and third derivative, are not very well behaved, because we basically threw them out of our Taylor expansion. But as long as the function doesn't have very large high order derivatives, this should work really, really well for finding our roots. So let's go try it. Once again, we have the equation x plus e to the negative 2x equals 1, and we're going to rewrite this in the form f of x equals 0. So we'll begin by defining f. Actually, will look exactly like it did when we did the binary search. So that'll be x plus x of negative 2 times x minus 1. And if we're going to do the proper Newton-Raphson method, we should also do the derivative. In this case, this is a function that we can differentiate analytically. So df dx here, we know exactly would have to be equal to 1 minus 2 times x negative 2 times x. Second here, okay, looks good. And now we're ready for our method. We need some initial guess. So if we guess 1, we should converge to the solution that's at 0.797. And we'll set up a for loop. You pick some number of iterations, 100, 1,000. This is also, like binary search, a pretty quick method, so 100 should be fine. And I want to check if I'm converging each step. Before we've taken the strategy of keeping all the values in a big list, kind of inefficient if you aren't going to do something like plot them. So let's just make a single variable. That's just the last value of x. I'll call it x last, and we'll set it equal to the current value of x. And then we'll update x by taking itself and subtracting f of x divided by df dx of x. And of course, we could write this as a minus equals. So take just a little bit of typing there, x minus equals f of x on its derivative. And then to check for convergence, if the absolute value of x minus the previous value is less than a tolerance, let's say 10 to the minus 8 is what we've been using, then we will print a success message like x equals the current value of x after I plus 1 iterations. And we will escape. And if we can't escape, then we'll print a failure message. Okay, so basically the same structure of code we've been using throughout this whole section, just using different methods. So let's see how quickly this one succeeds. Or if I made a typo, oh, look at that, I do have a typo. Return, got some missing parenthesis here. All right, oh look, it only took 5 iterations this time, so very quick. We have 0.797. Now let's look at SciPy's version of this. It's called Newton. And if we peek here, it needs a function, it needs an initial guess, and by default f prime is none. F prime is going to be the derivative term. I think I'll talk about it right here. So if the function derivative is available, then we can use it here. If it's not, then we're going to do the secant method, which means we're going to just numerically calculate the derivative based on evaluating the function and using something like midpoint rule. Okay, well let's start with, since we have the derivative, put that in here. So f prime is going to be df dx. And I don't have to type out the f prime equals, but it's just visually a nice reminder that that last argument is the derivative. So let's try that out, and we got 0.797. Let's see if we can find the other solution. You remember way back, this actually has another solution at 0. So I started a guess at 1, which was close to the 0.797 solution. What if I do negative 0.01? Well, we hit the other solution, and sure enough, within numerical tolerance, we get 0, the other solution. Now finally, let's look at this with the secant method. So to make this the secant method, all we have to do is exclude the f prime. And let's check. So we get 0.797, and you can see like it's, let's put this one back just so we can compare how much of a difference does it make having that derivative versus not. You know, we're out here where we get a little bit of rounding error out at quite a lot of decimal places. So it's usually not a huge deal to not have the analytic derivative. It depends on how well behaved your function is, really. But in most cases, you can get away without having it. And the secant method here works just fine.